Alright, so we're back to our classical mechanics book. I'm going to try to knock a few of these problems out. If you can't tell by my voice, I'm not feeling very good, so bear with me. Okay, so we want to show, 1.9 basically said if you had vector r equals a1x plus b1y plus c1z, and if vector s was a 2x plus b2y plus c2z, the cross product between these two vectors is equal to the determinant of, put our unit vectors up here, and then we just put the coefficients. We talked about this in one of the review videos, so if you're not okay with this, then I would recommend checking that out. Someone commented on a YouTube video, I'll read that later. So if we were to solve this determinant, which, again, if you're not sure how to do that, I would recommend looking through it, the previous videos. It's b1 c2 minus b2 c1. This is the x hat minus a1 c1 or c2 minus a2 c1 y hat plus a1 b2 minus a2 b1 z hat. So the big thing to note here is that this spits out another vector. This is the vector r cross s, which we could just call, I don't know, vector, let's call it vector v. Then, if this is perpendicular, so this spits out a vector, and this vector v is going to be perpendicular to both r and s. So if it's perpendicular, that means if let's take r for example, and we dot it with v, that's equivalent to r vector dotted with r cross s. And r cross s is equivalent to all this stuff. So that's equal to, well, our r hat is a1x plus b1y plus c1z, and we're dotting that with all this mess. So let's see, b1 c2 minus b2 c1 x minus a1 c2 minus a2 c1 y plus a1 b2 minus a2 b1 z. So the way we do this is we just take our a. If you don't remember how we do our dot product, we do the x component times the other x component plus the b component, well, the y component, I'm sorry, times the other z or other y component times z component times other z component, and we just add all that up and we see what we get. Well, if we were to do that, let's see, what do we get? We get a1 b1 c2 minus a1 b2 c1 minus b1 a1 c2 plus b1 a2 c1 plus c1 a1 b1, I'm sorry, yeah, b1 minus c1 a2 b1. Okay, I think I got all that down. Well, let's see if we can match terms here. We have an A1 a B1 and a C2. Can we find that anywhere else? Hopefully, because that would mean I misadded somewhere. Right here. So that means these guys drop. We have a minus A1, B2, C1. Now let's see, we need a C1, an A1, and a B2 right here. Yep. And then a B1, A2, C1 cancels here. This is supposed to be a B2. I think I said B1, but this should be a B2 because that's coming from here, and that's a B2. I don't know why I thought that was a 1. So this is all equal to 0. So what does that mean? That means R is perpendicular to V. And you can do something similar with S. I recommend doing that actually. But this shows that it's perpendicular. And then let's just talk about the right-hand rule really quick. We have a vector R and then a vector S. You put your finger in the directions of, so let's say we want to do R cross S, the order matters. You put your fingers in such a way that they go along R. And there's two ways you can do that. You can either do it with your thumb pointing this way or your thumb pointing this way. Now, the only way to curl your fingers in the direction of S is if you go this way. If your thumb's pointing, or your palm is pointing that way. Then you can easily curl your fingers. So that tells us that vector V would go into the page. And it's perpendicular to both R and S. That's the only way you can, and this might actually be a decent proof, is to go through, do the exact same thing with S dotted with V, see that it's perpendicular. There's only two ways you can be perpendicular to both R and to S, because R and S is in the XY plane. So the only way that's possible is if we consider it's coming at us or away from us. Towards us, into the page, or out of the page. That's the only way it'll be perpendicular to both. So hopefully that makes sense. That should at least help you.